Okay, first of all, I would like to thank the organizers for having me here. So today I will talk about vector tensor theories, yet another class of modified gravity theories. But before I do that, I wanted to start first giving you all the tools and knowledge that we already gathered by constructing Scalar-Tensor interactions, for instance, like the Galilean and Ondensky, and then also the tensor-tensor interactions like in massive gravity. I think it's worth to go through all this again, specifically to construct the tensor-tensor interactions coming from the decoupling limit. And in this way, we can then actually take exactly the same tools and apply it to the vector tensor case and construct the derivative self-interactions in a consistent way. And in this way, we can then construct the vector tensor interactions, this generalized PROCA theories, and if I have time, I will also mention their cosmological implications. Okay, so as you know, in the standard model of particle physics and also theoretical cosmology, we usually deal with the particles of spin 0, 1/2, 1, and 2. Maybe in cosmology, the spin 1/2, not so much. But so in this theory, I will be basically trying to modify that part of the PROCA action. But as I said, I will first introduce what you do with the spin 2 particle and the spin 0 particle. Okay, so let me start with the massless spin 2 field. So you can start with the easy question saying, what is the most general Lagrangian that I can write down in 4 dimension for a massless spin 2 field? We already know that these are the low-lock invariants, for instance, the cosmological constant, the Ricci scalar, and then the Gauss-Bonnet. In 4 dimension, Gauss-Bonnet is just topological. But if you were in 5-dimensional, etc., you could then construct in this way all these low-lock invariants. And related to the low-lock invariants, by calculating their equations of motion, you can then construct these divergenceless tensors. For instance, to the one corresponding to the cosmological constant is just the metric itself, then to the Ricci scalar, the Einstein tensor. And if you had the Gauss-Bonnet term, which was not topological, we could even construct another divergenceless tensor here by computing the equation of motion. So in 4 dimension, this uniquely then gives rise to GR as the unique theory for a massless spin 2 field. Okay, so if you now want to couple all the other matter fields to this massless spin 2 field, how can you do that? Well, you can either couple them directly to the low-lock invariants or to these divergenceless tensors that I just constructed. Sorry. There is yet another divergenceless tensor. This is the double dual Riemann tensor. And since it's also divergenceless, you can also couple the matter fields directly to that tensor. So you can write all the low-lock invariants and the corresponding divergenceless tensors in terms of the Levi-Civita so that you know how their structure come in. Okay, so but I will be modifying gravity, but I will be following the philosophy that we have a pseudo-Riemannian manifold. And I have Lorentz invariance, I want unitarity, etc. So I am faced with the fact that I have to introduce new degrees of freedom. This could be additional tensor, vector, or scalar. Okay. So as I said, I will go through this tensor-tensor, scalar-tensor theories first and pick up the tools that we need. And I mean, it's good that that people had already developed all of these tools. So it's really just maybe not even a fundamental thing, just an easy task to also apply them to the vector tensor case. Okay, so, but when I modify gravity, I don't want to exaggerate that. So I want these modifications really to come in only on cosmological scale. So I have to make sure that on small scales, I really recover general relativity, and there are different screening mechanisms. And for the vector tensor theories that I will be discussing, they have the similar Weinstein mechanism as, for instance, in massive gravity. Okay, so let me start with the scalar field. Okay, so it's worth to work with scalar fields because they easily give rise to isotropic solutions. So I can simply write down the Lagrangian. But I can also go a step further and I can write down some derivative self-interactions, which was done by these people here, these Galilean interactions. We have already seen them. I just want to pick up some very important properties of them. First of all, they stop after L5 in 4 dimension. They give rise to second-order equations of motion. And I can, maybe if I write them in terms of these Levi-Civita tensors, it becomes then apparent that all these classical theories are also stable under quantum corrections. Because this guy, this pi min u, which is the second derivative applied order scalar field, because this guy is symmetric, and now I contract it with the 2 Levi-Civita tensors. And when I now construct any arbitrary Feynman diagrams, this guarantees that all the quantum contributions that you get have higher derivatives per field than your classical theories. Yeah, so the Galilean symmetry will, of course, will protect them, but it doesn't protect from the fact that you can still construct exactly these classical theories and renormalize them. And if you have to tune their coefficients, then they might get some large quantum corrections. But because of this Levi-Civita structure, actually they don't. So they are technically natural in this sense. So can we generalize now these interactions to curved spacetime? Yes, we can, and we know that already. We have heard that several times, these Horndenski interactions. So I can basically take the flat case and put the converted the partial derivatives to covariant derivatives. So on that part here, you see just the covariant version of them. But I have to add this non-minimal couplings to either the low-log invariant term or the divergenceless tensor like the Einstein tensor in order to maintain that I have second-order equations of motion. I can break the Galilean symmetry, etc. So I need to add non-minimal couplings at this order in order to maintain the equations of motion second order. I guess I can use this. Okay. So let me now also discuss quickly the tensor-tensor theories. So instead of now adding a scalar, I want to add a tensor field into the game and ask the same question: how do they couple? So why do I need another second tensor? Well, if you want to try to write a mass term for the graviton itself, if you try to contract it with itself, you are basically just writing down some numbers. So you realize you have to introduce another tensor on top of which then the graviton, the massive graviton, can propagate, and you can contract the indices. So how can we construct in a consistent way this type of potential interactions for the graviton? And in order to answer this question, I will then start from the decoupling limit, as it has been done historically, and take the tools that have been developed there and apply that directly to the vector case. Okay, so if you make the graviton massive, you have now 5 degrees of freedom, 2 helicity 2, 2 helicity 1, and 1 helicity 0 degree of freedom. And your interactions have basically this form here, where you see the scalar guy comes always with second derivative, so it has the Galilean symmetry always. But you have the helicity 1 and then the helicity 2. And when you construct now these interactions, you have to make sure that this scalar degree of freedom doesn't give rise to higher order equations of motion. So let's start with the decoupling limit by sending the mass to 0, the Planck mass to infinity, by keeping this combination here fixed. And in this way, you can then construct the decoupling limit Lagrangian in this way, which is first order in the helicity 2 field, and it's multiplied by this matrices x min u 1, 2, 3. And these matrices, they have to satisfy a given condition in order to guarantee that only the helicity 0 degree of freedom propagates. So for instance, the xij can only have most 2 time derivatives. The x00 has has no time derivatives, and the x0I has at most one time derivatives, and the x mu nu is transverse. So by demanding these conditions, you can explicitly write down what this x mu nu has to be in order to have just second-order equations of motion for the scalar field. Okay? And this was what was done, and you see this x mu nu matrices in the decoupling limit, they just have very similar structure as we saw for the Galilean. So in terms of the Levi-Civita tensors, you can write them in this form again. Okay? So, and I was neglecting the Helicity-1 field. So once I construct the decoupling limit Lagrangian, I can then basically promote that to the beyond the decoupling limit Lagrangian, and that was done by Claudia Andrew and Gabarazze. So here you can do that by just promoting the pi mu nu object to this k mu nu matrix, which is given by in terms of this square root, in terms of this square root. Okay. So in the decoupling limit, you had some conditions on this x mu nu matrices, or in other words, if you just take the pure Helicity 0 part, it should be a total derivative. And then construct from away from the decoupling the full potential interactions. Okay, and they are nothing else but the elementary polynomials of this matrix K mu nu. Okay, so exactly this type of same methods I will also use for the vector tensor. Start from the decoupling limit, construct the interactions in the decoupling limit, and then promote them to the vector tensor theories beyond that limit. So here I have two metrics G and F, and a natural question is how do they couple to the metric fields? So one natural way is if they couple the G metric to a separate species and the F metric to another different independent species. In this way, if you couple that, the theory is classically stable, and it's also stable under quantum corrections. Sorry. But if you insist that you want to couple the matter fields to both of the metrics at the same time, then you can do that via this effective metric constructed in this very specific way out of G and F. So this effective metric is unique in the sense that the only effective composite metric that you can build that is ghost-free in the decoupling limit. Okay? If you construct any other effective matrix out of G and F, which is not that, which doesn't have this form, then it immediately yields to a ghost degree of freedom. Okay, so now I will use exactly the same techniques to construct the vector tensor theories. Let me start with what we already know about massless vector fields. Okay, so we know that massless vector fields have to be invariant under this gauge transformation. And this gauge invariance guarantees that at the end of the day, you will only have two propagating degrees of freedom out of the four components that you have in this vector field. And this uniquely leads to Maxwell-Lagrangian. In the same way as we were asking the massless spin 2 field that was giving uniquely general relativity, here we obtain uniquely Maxwell theory. Okay, and in the same way we could also now ask, can we construct derivative self-interaction now for this massless vector field, some type of Galilean interaction for the massless vector field? And the answer to that seems to be a no-go. Was discussed here in this paper. So if you are in 4 dimension and you have abelian gauge fields, then you cannot construct this type of Galilean interaction for the massless vector field. If you are in 5 dimension and you have a non-abelian gauge field, then you could indeed start to construct this type of Galilean interactions, but not in 4 dimension. And if you want to now couple this massless vector field to the gravity sector, that supposedly lives in curved spacetime, then you can basically just take the Maxwell action, put the square root of -g in front, that's fine, but you can also add some unique non-minimal couplings for the massless vector field. That was already also discussed by Horndansky himself. And you see this is again this divergenceless tensor, the double dual Riemann tensor, to which you then can couple the massless vector field. And it will give rise to the right propagating degrees of freedom, gives rise to second order equations of motion, etc. Okay. So how about the massive vector field? Now I want to break explicitly the gauge symmetry, so I am adding a mass term here. And I can ask the same question, can I have derivative Galilean type of interactions for the massive vector field that propagates the right 3 degrees of freedom, and you can get rid of the no-go result and construct these generalized Proca interactions. And the demand that you are asking is again that you don't have some higher order equations of motion for the helix D0 part of the vector. Okay, so let me start with the easy L2 part. At that level, I can basically just write down an arbitrary function that depends on the vector field, but also on the gauge invariant quantities like the field strength and the dual of the field strength. Because the temporal component does not contribute to this guy, and here because the temporal component doesn't have any time derivatives, so you immediately have just 3 propagating degrees of freedom, and A0 is not dynamical. So L2 is kind of boring. L3 is equally boring, I guess. So at that level, you can just write down this contraction here, and you can multiply it by an arbitrary function that depends on the norm of the vector field. You can write that in terms of the Levi-Civita tensors in the same way as we did with the Galilean interaction. So for that L3 case, the Heysen matrix just vanishes identically, but you have this function of the norm. It doesn't correspond to just total divergence term. But so in this way, you can also construct the L3 term. Okay, so let me go to the quartic order. So at that order, I can write down all the possible contractions, quadratic in partial A, basically, with arbitrary coefficients. And I demand again the question how I can make the determinant of this Hessian matrix to vanish. And I don't want to A0 propagate, so that I have 3 propagating degrees of freedom. I can do that by putting this combination here to 0, and in this way I will guarantee that I have a constrained equation that will remove the temporal component. Okay, so I have to pick up this condition for the coefficients, and in this way I obtain the 4th order Lagrangian. And you see you have this F squared term here, which was just part of L2, so I can't put that in L2. And at L4, I just have the standard Galilean type of interaction. And I can write them also in terms of the Levi-Civita again, but maybe let's remind ourselves that this partial A can now have its symmetric and anti-symmetric part, right? In the case of the scalar, the object pi mu, which was second derivative applied on the scalar field, was symmetric. And I had only one way of contracting them with the Levi-Civita tensor. But now, because this guy, this fundamental object here, has symmetric and anti-symmetric part, I have 2 different ways of contracting them with the Levi-Civita tensor, and they will give rise to 2 independent contributions. The part that comes from here, as I said, is just the F squared that I can then that I have already in L2, so I don't have to repeat it. And this uniquely gives then the L4. I can compute exactly the constraint equation associated to that, and the secondary constraint, and I can really see the A0, the temporal component, does not propagate. Okay, so I can do the same thing for the quintic order I think you see where I am going. I can just write down all the two possible contractions with the Levi-Civita tensor. And this gives me the L5 type of Lagrangians. This part here is very familiar to you, coming from the scalar counterpart. But you see here in L5, we have this non-trivial vector interactions that we have only in the vector case, which was not there in the scalar counterpart. In difference also to the scalar case, I can go just one order more. So the series does not stop at L5, but L6. So I can construct the sixth order Lagrangian with 4 partial A terms. And in this way, I contracted all the indices with my Levi-Civita tensors. And this uniquely then gives this type of vector interactions coupled with the double dual, not double dual, the dual field strength. And this again is pure vector interactions and doesn't exist in the scalar case. And the series stop at L6. Okay, so here are all the interactions for this generalized Proca theories. As I mentioned, if you take the A mu goes to partial mu phi, so you take the longitudinal mode, then all these parts here will give you the type of Galilean interactions that we know. But here you have also this F tilde 5 kind of term, and here the L6 that really is pure vector interaction. Okay, so I can construct exactly the same interactions also from the decoupling limit analysis in the same way as was discussing for massive gravity. So I can write down all my interactions. I can expand them in a similar way in this form with their given scaling. And this S is just corresponding to the symmetric case. F has with a minus and S is with a plus. So I can introduce the Stuckelberg field here. And now this pi will basically should correspond to the Galilean type of field. So the Stuckelberg field, of course, does not contribute to the F, but it only contributes to the A and S here. So I can systematically, in the decoupling limit, ask the same question as how can the pi couple with the F and with itself in a consistent way such that the pi field doesn't have any higher order equations of motion. So I can start with linear impartial pi, basically, and you can convince yourself that at that order, the only way of coupling this is either via a Galilean type of interaction with itself or with an F dual. And the reason is, if you write that in terms of, let's say, a matrix M mu, remember in massive gravity, these were our X mu matrices, and we had to put some conditions on this X mu, how they were supposed to depend on the time derivative. And in the same way, we can put constraints on this M mu. And for instance, the M00 shouldn't contain any other time derivative than pi dot. And so on. So in a similar way, by putting conditions on this matrix M mu, I can then construct my decoupling limit Lagrangian. And they can have basically just either pure Galilean interactions or this non-trivial interactions between the helicity 0 and the helicity 1 guy. Okay, so I can go to next order now to second impartial pi and ask again the same question and construct basically the conditions on this matrix. And it turns out, again, I can have at this level either pure Galilean type of interactions for itself or with the spin 1 field only via this type of interactions with the dual field strength tensor. Okay. Okay, and if I go now to third order in partial pi cube, basically, then you can see that there isn't any, you can't construct any sorry, you can't construct any direct coupling to the spin 1 field, but you can only have just pure Galilean interactions for the helicity 0 field. And the series stops here, so you can't go any further. So you can already see in the decoupling limit that the interactions are finite. And in this way, I can construct my interactions by going now beyond the decoupling limit by promoting partial mu pi to a mu and this guy to s mu nu. And in this way, I can just construct the same Lagrangians that I had previously. Maybe if you write it in this term, you can immediately pick up the longitudinal, the helicity 0 guy immediately. Yeah, I can write this interactions also in terms of some determinant where the C mu matrix is given by that, and then these are just then the elementary polynomials, of this matrix C. Okay. So then I can promote that to curved space-time. So how do I have to couple them to G mu nu in a consistent way? These are the generalized Procca interactions now in curved space-time. You see at L4 you have a similar, by the way, this Y is just the norm of the vector field. You have this non-minimal coupling again to the Ricci and to the divergenceless tensor, the Einstein tensor. So this pure intrinsic vector interactions here, they don't need any non-minimal coupling if you promote them to curved space-time. But for L6, for this guy, you need to introduce this non-minimal coupling in order, again, make the equations of motion second order. Okay? So you see, in a very similar way, you can also construct this vector tensor interactions. You can even do some cosmology with them. So if you want to have homogeneous anisotropic solutions, and if you have a massive vector field, just one of them, then you can do that just by having an ansatz for the temporal component, phi t here. And in this way, you will have a homogeneous anisotropic solution. Or imagine you have a non-abelian gauge field, so you have basically 3 copies of vector fields. Then by choosing the spatial part in this way, you can actually make also homogeneous, construct homogeneous anisotropic field configuration. And these vector fields, basically, they are orthogonal to each other, and they show along the spatial direction. And in this way, you have homogeneous anisotropic solutions. Or if you want, you can also do a la Mukhanov and have just a lot of n number of vector fields, and they point along any kind of direction. This could also give rise to a homogeneous anisotropic solution. So we have been considering the first one with the Procca, generalized Procca vector field, and in this way you can construct your Einstein equations, the vector field equations. What is nice in this theories is it's very simply very nicely gives rise to the de Sitter type of critical point. So wherever you start, you end up in this de Sitter critical point. And if you look also at the perturbations of this vector field and of the metric, if you look at the perturbations, the modified Poisson equation have now instead of G Newton, this G effective. And here is the plot of G effective versus G Newton. And this QV is just some parameters of the model. So depending on how you choose the parameter, you can actually realize very easily weak gravity in this vector tensor theories. So some people say it's kind of difficult to do that in the scalar tensor case, but in the vector tensor, this comes very, very easily. So you can have weak gravity. Okay, so you can also have now, you have Procca, you can also have multi-Procca. Imagine if you would break the SU2 kind of symmetry. So you can also construct the same type of interactions for a non-abelian vector field with their interactions. And if you do that, actually you have yet another third field configuration that you can consider that hasn't been considered so far in the literature, where you can also have the AI0 part coming in. The field configuration is such that the stretched energy tensor is still homogeneous and isotropic. Okay, so you can have definitely again homogeneous and isotropic background. Okay, so I gave you all these different modified gravity theories, and of course they will have different impact on the cosmological and astrophysical observations, and then the next or ongoing and next generation of observation. If you combine geometrical probes, structure formation probes, and then the astrophysical probes like gravitational waves. I think yesterday we found out that Horndenski type of theories are still fine. It would have been nice to kill all this scalar-tensor, vector tensor, and so that we could do real physics. Anyway, so we can combine all these observations, and then we will figure out what kind of models then survive after putting on trial by all these combined observations. Yeah, I think I stop here. Thank you.
You got a reduction in the effective Newton's constant. How does it work? What's the physics behind this?
Oh, the physics is very simple. I am modifying gravity, so I have all this.
But you do that also in scalar-tensor theories, where there's always an attractive force. But how does it work?
So the way how these interactions come in the G effective, unfortunately, I don't have the explicit expression in G effective. So in the scalar case, usually the way how the individual terms come is, first of all, they all come in a way that if you want to make weak gravity, you either have a ghost degree of freedom in order to make it sufficiently. I think people know that better. I think you were mentioning that on Monday, right?
Yes.
So you either have this, you have to pay the price that you introduce a ghost degree of freedom. But here the interactions, the functions come in a way explicitly, especially the intrinsic vector contributions, this f tilde 5 and G6 type of terms with the minus sign. And if you make the coefficient sufficiently small, like this QV, then you can push it down. You cannot push it arbitrarily down, otherwise you might have some strong coupling issues. But yeah, in principle, you can do weak gravity.
So do you recover the beyond Horndenski type things too? Do those maybe come from the f tilde terms or something like that? Or
No. This is so this.
If I just send it to like the scalar limit.
If I take a mu and I take a mu goes to partial mu phi, then I recover in this part the Horndenski interactions. But this is pure vector. It has nothing to do with beyond Horndenski or whatever. So this is really pure intrinsic vector interaction, and it doesn't have any scalar counterpart. You could also construct beyond Proca interactions. Yeah, the game never stops. I have myself a paper on it. I'm not proud, but yeah, you can do it.
And Proca dehost. Okay.
So did you also write down the Higgs version of this, because that should be pretty easy to do?
Yeah, Higgs version, yes.
Because that'd be like a two scalar Horndenski thing, gauged.
Yeah, I think Gian Massimo has.
Did he do that?
He has some nice papers on it.
So, in this theory, what kind of terms would produce an anomalous speed for gravitational waves? Because I see a lot of non-antisymmetric derivatives.
Yeah, I mean exactly the same types as in Horndenski. So this one and this one, but also this L6. Yeah, you have even another function that also comes into the tensor perturbations. maybe because you have more functions and freedom, maybe you can play a little bit better, but they also will give rise to anomalies, gravitational speed.
What about the D5 tilde?
This one?
Yeah.
This one, yeah, this one might also. Yeah, I think all of this, starting from L4, they will start contributing. Yeah.
So, in order to have homogeneity in the isotropy, you make a choice on the configuration of the vector fields. So how natural is that choice that you make?
Oh, how natural. To me, it's very natural, but it's in the same way. Okay, if you have a scalar field, the natural ansatz is it just has a time dependence, which you just break the time diffeomorphism, right? And here in this case, you also ask the same question. I have my Poincare symmetry, and I want to break it, the time and boost, and this field configuration naturally does that. So if I pick it up in that way or in that way, I end up doing the same type of symmetry breaking pattern. I mean, in this case, it's natural, yes.
But what about having a wave of this vector field?
If you have like the spatial part of it? Or?
Yeah.
Yeah, if you have a spatial part, then you can use this vector field only as a small test particle, but it shouldn't back react on your metric. Then you will have anisotropies at the background level already.